Chapter 2, Section 2, Scientific Method. The scientific method is a logical approach to solving problems by, and these are all the things that make up the scientific method, and we're going to talk about each of these individually throughout the set of notes. Observing and collecting data is one. Formulating a hypothesis. Testing hypothesis. Formulating theories. And this is supported by data. Now, I think one of the most important things to mention about the scientific method is that it is not a fixed series of steps. Okay? So if you think about the mystery solution lab that we're doing in this chapter, what we actually did was we did some testing first, we made some observations, and then we formulated a hypothesis. Okay? So again, not a fixed series of steps. Okay? So these are all the parts that make up the scientific method. And this image is also in your textbook on page 46. And the one thing that's listed here that was not on the previous slide is publishing results. So one way scientists publish the results is at symposiums, so giving some kind of oral presentation, or even having their work published in some kind of journal. So we're going to look at an animation, and the animation is going to give us an overview of the scientific method, and then we'll talk about each of the parts individually.
Follow these 7 basic steps of the scientific method. First, scientists make observations. For example, paleontologists observe fossilized dinosaur remains in order to learn about dinosaurs that once roamed the earth. A scientist's observations often lead to questions. Upon discovering a set of fossilized dinosaur bones, a paleontologist would likely ask, what kind of dinosaur do these bones come from? A scientist often investigates a question by forming a hypothesis. The paleontologist in this example hypothesized that the bones he observed come from a type of dinosaur that had not yet been discovered. Scientists test hypotheses by gathering data that can help determine whether the hypotheses are valid or not. Once scientists finish their tests, they must analyze the results. An analysis of the dinosaur bone measurements and the comparisons might show that the new dinosaur bones are either too large or shaped too differently to have belonged to any of the comparison dinosaurs that have already been discovered. Or the tests might show that a dinosaur matching the new bones had already been discovered. Finally, scientists must conclude whether the results of their tests supported the hypothesis. Let's suppose that the dinosaur bone measurement tests led to the conclusion that a new dinosaur species has been discovered. Upon completing an investigation, scientists communicate their results. Scientists often present their findings in speeches, journal articles, and books.
All right, so let's talk about observations and collecting data. So when we talk about observation, we're talking about using our senses to obtain information. Data collection really falls into one of two categories. Okay. Data can be qualitative, which means some kind of description. Okay. State of matter would be a good example. Color would be an example. If we're looking at chemical reactions, we could talk about noticing that bubbles are being produced. The other type of data is quantitative. This quantitative data has a numerical value and a unit. So if we think back to the lab techniques lab that we did in the opening chapter, we recorded the volume of water in a beaker, the volume of water in a graduated cylinder, the amount of salt on a balance. So all of those would have had a numerical value and a unit. And then within our lab report, we take that qualitative and quantitative data and we put it into some kind of table. And then when we go to analyze that, we make it into a graph so we can see relationships. So if we think about the lab techniques lab, we looked at the relationship between mass and volume of water. Part number 2, formulating a hypothesis. Okay. So a hypothesis is some kind of generalization about our data or observations. So if we think about the Mystery Solution Lab, we recorded our observations. These were qualitative observations. Okay? We saw cloudiness. We saw bubbling appearing, or in some cases we saw nothing happen. Okay? Then you and your partner had a discussion, a written discussion, to compare your data and made some kind of hypothesis. You said that this letter is equivalent to this number. Okay. Number 2, a hypothesis is a testable statement. So if we would have given your sets of solutions from the Mystery Solution Lab to another group, they should have been able to test your hypothesis. It's often in an if-then statement. So if we think about the blue ice lab from the first chapter, we could have made that hypothesis into an if-then statement. Okay? If the ice cube is placed in salt water, then it will take longer to melt. Okay? So a prediction that is the basis for testing by experiment is really the definition of a hypothesis. Testing a hypothesis. Okay? So this would be our experiment. So our experiment has a control, conditions that remain constant. So for example, I used to teach environmental science, and we did a plant growth lab. So if we're talking about a plant growth lab, we're only going to change one variable, okay? And all the other variables will need to remain the same. Okay? So for example, the amount of sunlight, the amount of water, the amount of soil, those would all be things that would need to remain constant. Okay. The variable in that lab was seeds were exposed to radiation. Okay. So we would set up 2 sets of plants, one that had been exposed to radiation and one that had not been exposed to radiation. But the amount of soil, the amount of water, the amount of sunlight would all remain the same. And we would kind of start that lab off with a hypothesis. So if the seeds were exposed to radiation, and then the rest of it would be our prediction, these plants would not grow as fast. And again, the important thing to note about that experiment is that we were only looking at one variable at a time, the amount of radiation exposure. Okay. So theorizing. Okay, so we've had this experiment. We had a hypothesis. Our experiment verified our hypothesis. And if we have several other scientists who perform the same experiment and come up with the same results, then we make a theory. Sometimes theories are explained using a model. A model in science is more than a physical object. It is an explanation of how phenomena occur and how data or events are related. Okay. So in other words, a theory is a well-tested explanation of observations. So because theories are explanations, not facts, they can be disproved, but can never be completely proven. Okay. So we're going to see throughout chapter 3 that a theory is the atomic theory. Okay. And we're going to see how the atom has evolved over hundreds of years. So we're going to look at an animation that talks about several models in science. They do not all have to do with chemistry. So you're going to see various branches of science: earth science, physics, chemistry.
Models are used to represent things that are too small to see, such as atoms. Models can also represent objects in the solar system that are too large or far away to observe in certain ways. For example, this model can be used to show how the movements of the Earth, the Moon, and the Sun result in the different phases of the Moon. Scientists and engineers use computers to model systems and processes that are too expensive, complex, or dangerous to test in real life. For example, computer simulations use data related to ocean temperature and weather patterns to predict El Niño events and decide when to evacuate citizens prior to a hurricane making landfall. Models can also be used to represent ideas, concepts, or theories. For example, scientists noted that a rolling object, such as a push lawnmower, veers when it encounters at an angle a surface that slows it down. Light similarly veers when it passes from an easy-to-go-through medium, such as air, into a thicker medium, such as water. Scientists use the lawnmower model to help explain why light might exhibit such a behavior.
So we have a theory, and sometimes models are part of that theory. It is a broad generalization that explains a body of facts or phenomena. So itself is not a fact, it just helps explain the facts. And it can be modified with new discoveries. So what we're really looking at, how this ties into chapter 3, is we're going to look at the atom, and we're going to see how experimentation such as those by Thomson and those by Rutherford contributed to our modified versions of the atom. A law is a statement or mathematical expression that reliably describes the behavior of the natural world. So a theory is an explanation to explain the cause of certain events in the natural world, but a scientific law describes the events. For example, a scientific law would be the law of conservation of mass. If we were to make a prediction based upon the law of conservation of mass, we would say that the mass of my reactants is equal to the mass of my products, because I still have the same numbers and types of atoms, but what happens during a chemical reaction is the atoms themselves are rearranged. So one of the things we're going to look at in this chapter is a lab. We're going to combine vinegar and baking soda and measure the mass of those reactants. And then we're going to close up the container and we're going to measure the mass afterwards and see that they're the same. Okay. So our idea about what's going to happen in that lab is based upon the scientific law. In regards to laws being a mathematical expression, we're going to see second semester gas laws. Each gas law that we talk about is going to look at a mathematical relationship. For example, Boyle's law is a mathematical expression that looks at the relationship between pressure and volume.